Again. All right, so last time we had basically finished the idea of sort of introducing the Axion, which was, at least my favorite way of describing it, is just being carbon dioxide, except for quantum field theorized instead of just quantum mechanics. So we had said, done the first step, which was write down a theory that y GG tilde. Why is this coupling? Basically, we've seen this type of coupling before, and so all we have to do is duplicate what we've already seen, which was namely, we've seen the pion. The pion has exactly this sort of type of coupling, except for the photons instead. So all you had to do was say you had QCD with your pions and your E and M. All you had to do is relabel this to some new QCD. The pion is an axion, and E and M is replaced with QCD. And basically, the theory just goes straight as you would have said before, with chiral perturbation theory now of the new QCD giving you the axion instead. So what we're going to do next is basically say the opposite of before. This was why did you have a GG tilde, and why nothing else. And okay, so
sorry, just
yeah.
a quick question for you.
Yep.
Is there other string theory realization of scenario one? Is it like ubiquitous in?
So great. So if you want to say, how do I get this from, let's say, something a little more string theory like? So there are a few ways to say this. One is this is a composite axion, composite, and from ADS CFT, this is ADS. And so clearly, any theory that has a fifth dimension can do something similar to this, which is essentially just a statement that when you compactify, just compactification, compactifying this gives you extra scalars, namely in the form of A5. Compactifying two index guys, B mu nu, will give you both vectors, A mu 5, and I guess this is anti-symmetric. But if you do the symmetric version, you would also get some scalars. And continue to write, you just get lots of scalars. And it turns out that those guys can easily give these terms via Chern-Simons interactions. But
you're saying KK towers will provide.
Yeah, but usually that's the statement is KK towers give you this, and you might have to choose boundary conditions so that the scalar is light.
This extra gauge group, I mean this new SUN.
Great. So usually what they do is they say the axion is a A5 of a U1, and QCD is its own thing. So in other words, they don't try to combine or unify the axion with the gluon. They just say they're completely separate. Yeah. So I think actually in Tony's talk 2 days ago, yesterday, that was actually one of the, he went through it pretty quickly, but that was a term like that. That was a Chern-Simons exactly of that type. Yeah. Okay. Great. So first, why nothing else? So there are unavoidable terms, namely terms that you can get via RG evolution. These turn out not to be a problem. So what else? You will get additional terms, which are d mu a j mu over fa via RG evolution. So even if you set these guys to 0, you will generate them by RG. These are couplings to any sort of currents, yup type, up quarks, down quarks, etc. I guess they tend to be axial currents. But these are all generated by RG evolution, but they also don't provide a problem because you'll notice these are shift symmetric. So they do not give a potential for the axion. So all of these terms give you d of a equals 0 because these terms respect the shift symmetry. A go to a plus epsilon, and any mass term does not respect the symmetry, and so nothing happens. So RG evolution, no real problem, but this gives you a whole class of terms which you can write in addition to these GG tildes that just are there, and for example, you could use them to look for the axion, but they're not a problem. What are a problem are terms where you just write down by hand V of A, which is not centered around the origin. So we had said the axion has a potential that's centered around, I guess I'd phrase it as minus theta bar. I could just add another term that's over here. This is delta V. And that's a problem because this will just shift you away from the origin, right? And we have measured this guy, in the context of the axion, we've measured A over FA plus theta bar to be less than 10 to the minus 10. And so this minimum of this combined potential has to be much smaller than 10 to the minus 10. Okay, so why is it that you expect this to be non-zero in general? So to do it first, let's just give an example where even the effect, so not QCD anymore, I'm going to say, I'm going to change QCD just a little bit just to sort of make a point of why these delta V's are generic. But I'm going to write a version of QCD for which this is absolutely unavoidable, which is, let's look at QCD with, instead of the standard model, which has 6 flavors, I'm going to add another 6 guys. And the claim is changing nothing else in the standard model, just adding this. It is absolutely unavoidable for to introduce delta V. In particular, we'll actually need counter terms. So just to see, so I guess, yeah, this was actually in Tony's talk last time, but let's go over very briefly about instanton contributions to V. So this is V from instantons at a scale larger than QCD. So I'm going to look at the dilute instanton gas approximation coming from instantons of a scale larger than lambda QCD, so I have perturbative control. You can do this basically by dimensional analysis. You have the size of the instanton, d rho. I'm going to put rho to the 5 here to get the dimension 4 correct. We're going to have the instanton action, e to the minus 8 pi squared over g squared. And then you're going to have a product of zero modes. Zero modes, which are something here that we have to deal with. Okay, so let's just very, very quickly, go over this. Where's the? Okay, so the idea of instantons is pretty simple. When you do the path integral, integral dA, e to the I action, you have to include all paths here. And some of the paths happen to have an action 8 pi squared over g squared. And these guys are important because they are the ones that are theta dependent. So you really write plus I theta, and then hence why the axion appears. But also what's important in the path integral is some fermions. And normally what appears in a fermion action is e to the I integral psi bar d psi. And which, because fermions are nice and simple, I'm being somewhat sloppy here, d4x, etc. I probably don't have the i's right. Yeah, I don't have the i's right. But the point is, there are things called zero modes for which this equals 0. In other words, d slash acting on psi is 0, which means you have a fermionic integral of 1, which is 0. So when people say zero modes, they mean they're zeros of the Dirac equation. And the result of this is that the path integral is 0 unless you do insertions. In other words, this is equal to 0 unless you say, let's add a mass term, plus m psi bar psi, Taylor series this down, m psi bar psi. Now the integral is non-zero, and you can eat up a zero mode. So people like to draw these things schematically. Schematically, this is your instanton, and you draw out your number of zero modes. So like your up quark, Q, you have different generations, two of these, etc. And you contract them by doing Taylor seriesing in your exponential. And in the standard model, the relevant thing is your Yukawa matrix, Q, H, U, or your Yukawa matrix, Q, H, D. One of these is daggered. Let's say this guy is daggered. Okay, and so this means that what is Taylor seriesing this? This is just contracting these guys with a Higgs. So this is other guy with an H dagger, which then you can do connect again with the two-point function. So this is a slightly, well, still very fast, but slightly slower version than what you guys heard yesterday or the day before, which is instantons. This is sort of can get contracted with Yukawa couplings, y up here, I guess y down here. And so this just says the effect of all these zero modes is, let's say this is one generation. You add a yu, yd, and some pi's. So this is basically product of Yukawa couplings here to some power. And basically we have the answer by dimensional analysis here. Okay. Now, if you haven't worked it out, I very much suggest you to do so. I had said this a little bit before. Minus 8 pi squared over g squared is your confinement scale to the beta times some RG scale. In this case, you have the size of the instanton. So that's pretty naturally the size at which you determine everything. So rho, the beta power. What is your beta function? 11/3 NC minus 2/3 NF. Let's see, this is 12. This is 3. That's 11 minus 4. 11 minus 8 is 3, looks like. Okay, so the third power. So what do we notice about this here? One, this is greater than 0. And so QCD is still confining in the IR. But you'll notice here, this integral is an integral d rho over rho squared, which is UV divergent. So in other words, this theory needs a counterterm for the vacuum energy of theta. In other words, not only do you have the QCD contribution, which is nice and good, you need a counterterm for your theta dependence, or the vacuum energy of your theory. So it is not only often the case that delta V will be non-zero. In this case, it is required. I don't even need to appeal to anything else. You already have a counterterm. And where is everything centered? God knows. And so it's basically UV dependent. Okay, so that is, in some sense, maybe an overly complicated example of why delta V is non-zero. But it is also, there are plenty of other reasons. The basic reason for why it turns out to be non-zero here is that this is not a symmetry. We had said there is no symmetry forcing AGG tilde to be the only coupling, right? The best thing we had was this U1A symmetry, where the axion A over F is to A over F plus epsilon, theta goes to theta minus epsilon. And this is not a symmetry. This is a spurious symmetry. And so there is no reason there's no symmetry reason enforcing this to be the case. It's just the accidental symmetry of your theory. And anything with all accidental symmetries are just accidental. And so you should be able to write down a lot more. And let's see. Let's sort of, okay, and so in fact we've seen this already in another context. So in the context we did before of saying, in some sense, what was the most boring thing you can try to do is you can try to make the axion like the pion, right? So you have SUN, SU3, Q conjugate. I think I called it psi C. And you'll notice I did not write a mass term here. To get the pion, which is effectively the axion, I required there to be no mass term. However, there really is no reason why I couldn't write to my Lagrangian M1 Q conjugate or M2 psi conjugate. And as soon as I write this down, I'm in trouble. Because this gives a mass to the axion. And in particular, if I put a phase here, e to the I theta m1, we had said QQ conjugate was, morally speaking, e to the I a over fa, maybe with factors of 3 and factors of n in there. And you can see this is minimized around where a over fa is of order this theta m1. And so clearly this has nothing to do with theta QCD, and I'm boned. There's nothing.
Another question also.
Yeah.
What happens to the other pions? You will have a lot of them.
Yeah, so great.
Also, so
Every single other one is charged.
everything is charged.
So let's see. We can go through this pretty quickly. If this is Q C, psi C, Q psi. So there is the 1, 1, 1 minus 3, which is the axion. There is the octet of everything else in here, but that's going to be an octet under color now. So if these guys are sigma, is an octet under color. And so they will be massless at tree level, but then get a mass at one loop. So much like why the pi plus pi minus is heavier than the pi 0, there are electromagnetic corrections, in this case QCD corrections, to anything charged. You'll notice there's a Q psi C, so there's a triplet here, and a triplet here. So then there's a triplet. One is T prime, which is triplet, which also gets a mass. And looks like that's it. You can even count to make sure. There's 8, there is 6, and then there's 1. That is 8, 6, that's what, 15? Is that what I expect from, I guess, an approximate SU4 down to SU4 diagonal? That's 15, yeah. Okay, so I've counted them all. Okay, great. Yeah. All right. So in this case, you can just see I explicitly did not write down dimension, all of the low dimension operators, and that's basically the only reason why we solved the problem. Okay, so that's a problem. You can just imagine by hand setting masses to 0 is as bad as just by hand setting theta to 0, right? I'm just by hand setting stuff to 0 for no reason. So we clearly, in some sense, need to solve this problem and do something better. So there are many ways to do this. So since we're doing composite, one way to do this is if you still want to do the whole idea of oh, the axion is some pion-like object. We just need to write a more complicated theory where all the lowest dimensional accidents have U1A as a symmetry. And then it's only like a dimension 5, dimension 6, dimension 7 operator that accidentally breaks it. So people have done this. Where did I put everything? Oh, it's over there. Okay. And it's not super enlightening. I will write it down just for posteriors. For posterity here, just to see how complicated you have to go. And then you can make your own personal judgments for if it's too complicated to believe. To M, you have Q1, Q2, you have 3 quarks, you have 3 M of these, you have M of these, and you have 3 of these. 1 box. So, and wait. Okay, so what is happening here? These 2 guys are confining. You have two guys. N is vector-like, M is vector-like, so we know how they confine by chiral symmetry breaking. You get a whole ton of pions, much more complicated than this here. But one of them turns out to be massless, PQ, 1 minus 1, 1 minus 1. But you'll notice by the structure of the theory, it's pretty clearly chiral, so I can't write any mass terms. If I try to write Q1 with Q3, I can't satisfy the M index. If I try to do 2 with, let's see, 2 with 1, I don't get the SU3, etc. And the highest thing that breaks this accidental PQ symmetry is Q2 to the nth power and Q4 to the n over whatever, Planck scale, so 2m minus 4, I guess. Okay, so, all right, this is basically what you have to do, or some version of this, something like this, which is you say, EFT tells me I should write everything allowed by symmetries. This PQ symmetry is not a symmetry, despite the fact that everyone calls it the PQ symmetry. It is not a symmetry. It is an accident because theta transforms. And changing mass or parameters of your theory is not a symmetry. And you have to work hard to make it a higher dimensional operator. There are slightly more elegant ways of doing this once you're giving up this whole pion-axion connection, or maybe you just go to the strong coupling and say it's an extra dimension. But this is the basic idea. Let me think. I guess it's worth mentioning very briefly what sort of numbers to expect, like how large M and things like that have to be. Let's see. Okay. So let's just say, okay, it's easiest. Well, I guess we can just do it in the context of that model. These things confine and give you at the scale 4 pi f. So delta L, 4 pi, your confinement scale, Fa, to the 2mth power over m Planck to the 2m minus 4. And if this is aligned around a random point, this delta V should be 10 to the minus 10 times smaller than your axion. So this should be less than 10 to the minus 10 m pi squared f pi squared. In other words, 10 orders of magnitude smaller than this other guy. And so we can solve for m given some Fa. Let's see, I guess Ben was telling us yesterday about strings at 10 to the 11 GeV. Let's put in 10 to the 11 GeV. This is m Planck to the 4th. 10 to the 11 over 10 to the 18, 10 to the minus 7 to the 2m, 7 10 to the minus, let's put in units. This is 100 MeV, so 10 to the minus 4 GeV to the 4th. M Planck is 18. 18 times 4 is 72. 10 to the 72 GeV to the fourth. You can cancel this. You can see now why you needed something exponential, because these numbers are pretty ridiculous. 82, 86. 10 to the minus, or 7 times 2m is 14. 14m is less than 10 to the minus 86. Okay, that looks like what, 4, 5, 6. Okay, so this looks like m is larger than 7. So that's the sort of thing you need. You need slightly larger order 1 numbers in general. This is true for all solutions to this problem. You'll need some order 10-ish number to work in your favor. Basically, QCD is exponentially small, so any other exponentially still has to fight the QCD cage coupling at the Planck scale. Okay.
QCD will be very asymptotically non-free.
Yes, and it'll confine almost instantly in the UV, and which you don't want, because that breaks SU2, and so you're going to have to throw in new physics very, very quickly.
Also, the UV instantaneous
Yes.
very, very large.
Yep. Yeah, and so UV instantons make any story along these lines much harder. And so it gets even uglier. Okay. So basic idea, this is a problem. There are ways of solving it, but I don't know. Extra dimensions is actually a great way to do it, but in the end, you have to work hard. I think moral of the story is you don't write one new particle, one new coupling, right? You had such a great idea, the Axion, one new particle, one coupling. You could complicate it more and more, but as soon as you wanted to satisfy everything, it gets quite involved. So if you really want to push people, usually, at least I would say, every full UV completion, to me personally, has a few issues. If nothing else, just minimality.
What would your complaint of the fact that you UMD?
I think minimality probably, mainly. In some sense, 5D is adding an infinite number of new particles because momentum in the other direction in the KK states. Well, and whether or not that makes you happy, sometimes infinity is 0, sometimes it's not. That's what quantum field theory taught us. And so maybe that's an example where adding a lot is not actually adding much. Extra dimensions, I think, is probably the best, the one I like the most, if push comes to shove. Yeah, and just, I guess, since extra dimensions got brought up, very, very briefly, the idea of extra dimensional axions is you have a m, which is your a mu, and then an a5. And what you basically say is the axion is integral dx5 a5. And the way sort of the quality problem manifests itself here is that the d mu f mu 5 is j5. This is, roughly speaking, box of a5. You can integrate both sides dx5 to get box axion is integral dx5 j5, which means you have a circle here. You're taking an electron, running around the circle here, and we all know this effect ends up going as e to the minus mr. And so if your mass is larger than the size of the extra dimension, you get exponentially suppressed. So this is sort of the extra dimensional way of saying why suppressions, additional effects are suppressed, because it's non-local in the extra dimension. And so protected by locality. All right. Well, also you can rephrase that as using these higher form symmetries, and talk to Nathaniel if you're interested about that. All right. So let's move on and start talking some other aspects of the Axion. Since I enjoy it a lot, and this whole approach, a lot of this approach came from work done from ideas that were formed at KITP, let's talk about Axion strings. Okay. And why they are exciting field theoretically. Okay, so what is the idea of an Axion string? The Axion, the whole point of the Axion was to be like theta QCD. And so if QCD is an angle, this means your Axion is also an angle. It is periodic. What this means is that there is an origin, right? Any angle has an object, which is the origin around which when you go around, the angle goes to angle plus 2 pi. And in this case, the Axion is an angle, so you can do the same thing. The Axion here, a over f, goes to a over f plus 2 pi. And this object here is, well, it's a point in the xy plane, but it extends infinitely in the z direction. And so this is called an Axion string. An Axion string is just the origin of the Axion angle. Okay. So you can do it in any of these UV completions, KSVZ, DSVZ, composite, whatever. Most of them, well, they'll all sort of have this feature. It's a little more complicated for string theory axions, so I won't talk about them. And these guys have some very nice properties. So, okay. So, one, effects are all topological. So, this is a fun thing. Let's say we have an Axion string. Actually, let's just make it a loop, just so I can draw it better. And axions, as you go in around the circle, A goes to A plus 2 pi f. And this has very interesting effects on, let's say, your axion, your light. So this coupling, A over f, I'm going to write it normally. 1 over was the normalization. I think it was 16 pi squared, ff tilde. Okay, and so what is the effect of just this on, let's say, light even? So you shine light, it goes through your loop, so it transitions from A to A plus 2 pi. And so if you look at the dispersion relationship of this photon, you get the normal omega squared minus k squared equals 0. What you do is you add a piece here. You get, it's really much easier if I did this in time instead of space. That's a bummer. Okay, so the main point of this is that this is E dot B. And so as a photon comes through, its E field is turned into a B field. And so if you have light going in this direction polarized like this, that means its E and B are like this. And if E turns into B, you now have something whose B is here and E is here. And so we call this polarization rotation. You've taken this and you've rotated it. We're going off of the gradient of the axion field, so there's no energy deposited. It's just momenta. And the effect of this is to do polarization rotation. And if you actually go through the math here, this is, because it's a topological coupling, it's perhaps not surprised that it doesn't depend on your path. It just depends on your change in A over F. And this gives you a polarization rotation. Well, I'm going to write it like this. So cosmologists will call polarization rotation alpha. We call alpha the fine structure constant. Structure, this is polarization rotation. And you get an effect that is proportional entirely to your anomaly coefficient. So this is sort of, well, times 137, or divided by 137. And so if you knew things like the polarization of your initial photon, and it flew through or around an Axion loop, or Axion strings, you get effects that are measuring directly your 't Hooft anomaly, which really tickles the theorist in me, as does actually this equation, because it shows if you were sloppy, you would have gotten roughly the right answer anyways, but yeah.
I also heard from Chanda about these lumps of coherent axion.
Yep.
Which aren't really topological.
Yeah, that's correct.
So they would not produce such a rotation?
Correct. So this effect depends only on your initial and final states. So if it's easier if I write it as just a function of time, if this A dot over F K plus or minus depending on if you're circularly polarized. And the phase rotation is integral delta K dx, which in this case is just A over F, A dot over F dt times some speed of light, which is just delta A over F. So all of these effects are basically depend on your starting point and your end point and nothing else. So if you shone light through one of these lumps, or even through some overdensity of dark matter or whatever, you get no net effect. On the way through, it'll be slightly rotated, and then it gets rotated exactly back as it escapes. Yeah, which is an annoying feature since it makes things hard to see. It also makes it a little more robust, but like this effect, for example, you'll notice is completely independent of FA. FA, RG evolves, it has all this annoying stuff, but this is just going to be some topological, like this is actually related to the quantization of electric charge, for example. So if we saw CMB light passing through, get rotated by percent level, we could say something about the structure of quantization of charge in the standard model.
You call that a Hooft anomaly coefficient, but it's an AVJ, it's the AVJ anomaly
Yeah.
coefficient.
Okay. Actually, well, since it's fun, and this is the joy of physics, let me just tell people why this is related to quantization of electric charge. It turns out to be quite simple and easy to work out. So why are anomalies basically, or why is the periodicity of theta? Because that's what this is, right? If I have shift A over F by 2 pi, this is plus theta. If I shift A over F by 2 pi, this is saying theta is periodic by 2 pi times the anomaly coefficient. And my claim is that is telling you quantization of electric charge. So let's prove it for a U1, and I may or may not do it for the standard model. Okay, so if I have a theory, and with a photon plus electron, that's all there is to it. I can have a theta term, theta e squared over 16 pi squared, ff tilde. There is also the plus e a slash psi bar psi. Okay, so let's say I treat the electron as having charge 1. And you could just be like, okay, everyone tells me theta is 2 pi periodic. So theta equals theta plus 2 pi. Great. What we can do next is be like, well, I might have called the electron has charge 1, but the experimentalist over there called it charge 2, right? So, but we're studying the exact same theory. So this is experimentalist 1. Experimentalist 2 has basically E goes to 2E, right? Let's put QE here, QE. So this guy has QE equals 1, this guy has QE equals 2. Okay, so this guy is saying, well, this is equal to plus theta E squared over 16 pi squared, FF tilde plus QEE psi bar A slash psi. Now, this guy, because they measure the same force between the electrons, they're the same thing. Changing charge by 2 is just a matter of convention. This guy's E prime. E prime is Q times E is what, a half? E over 2. E prime over 2. Okay, and that means this guy would have thought his theta prime is theta prime plus 2 pi. But you'll notice these two things are not consistent, because if I set E goes to E over 2, this means theta prime is 4 times theta. One guy thinks that it's 2 pi symmetric. This guy thinks that it looks like it is, what, 8 pi symmetric by comparison, just by renaming what you call things. And so it turns out that the true periodicity depends on what is the full fundamental quantization, the full quantum, like the smallest measure of electric charge. And so that, it turns out to be basically what breaks this degeneracy. You can't, for an E and M in particular, this is only true for E and M, not for QCD or SU2. You can't just claim theta is 2 pi symmetric. You have to be careful. In particular, you have to be careful of your normalizations and what has charge 1, what has charge 2, and what is the actual fundamental value of electric charge. Because theta equals theta plus 2 pi only for the charge you put here, which is the smallest value of charge allowed by your theory. Yeah?
So in the standard model, the smallest value of charge is a third.
Depends.
Okay.
Okay, so yeah, let me just say, how does this manifest itself in the standard model? So here, let me just mention one quick way of seeing what's the real periodicity, which is you take your theory and you just put a Gedanken thing, which is you add to it psi minimal, which is the guy that has Q equals 1 and just write E minimal here. Minimal, whatever, I can't spell. Okay, and what you can do is in the path integral, E psi minimal, and this approach is going to generalize. Is you say E to the I action, this is equal to 1 times itself. I'm going to do a field redefinition of psi equals psi. Obviously, that changes absolutely nothing. But I'm going to write 1 as E to the 2 pi I. And now you will say I have changed it, because I have done an anomalous rotation. Instead of multiplying by 1, which obviously does nothing, I'm multiplying it by E to the 2 pi I, which also needs to do nothing because it's 1, but is an anomalous rotation. So this is integral d psi min E to the d4x 2 pi theta equals 2 pi 1 over 16 pi squared E minimal squared ff tilde. And now we had said this has to be 1 because I'm multiplying by 1, which means this guy here is equal to an integer. you get e to the 2 pi I times an integer. So if you want the cleanest and quickest way, the lazy man's sort of ABJ anomaly way of doing things, this is how you get the periodicity of everything. And what determines what this integer is what you allow psi, the charge of psi, the minimal charge allowed in your theory. Now, standard model is slightly different. Let's write it down. So the standard model, SU3, SU2, U1, you have Q, U, D, L, E. Okay, I can't remember if any of these are barred, but okay, I can never remember the lepton. It might be -1/2, but okay. Now you can do the same trick. I had said, right, periodicity of theta is you put in the minimally charged object and then multiply it by 1 in the path integral. Let's do this for the standard model. Okay. So, great. Let's do it for Q. Integral dq e to the is is integral de to the 2 pi I times q e to the is, which is integral e to the, okay, I'm doing a full 2 pi times, put an I here, integral d4x. Okay, so there's gg tilde over 32 pi squared. There is, let's call it ww tilde for SU2. But this thing has charge 1/6. So you say plus 1/6 squared dv tilde over 16 pi squared. Okay. Now, this obviously all has to be an integer. But you have several options to make it all an integer. You can say, this is an integer, that's an integer, that's an integer. If you did that, you'd be like, theta looks like it's 2 pi over 6 squared periodic. Right? That's all you have to conclude that. This is an integer, this is an integer, must be 6 squared times an integer. The other option is to say, not an integer, not an integer, not an integer, their sum is an integer. And so these different things have different names. So for example, if everything is an integer, like all integers, so all integers implies the standard model gauge group is SU3 times SU2 times U1. If you say not an integer, not an integer, not an integer, but adds to an integer, what you say is, so sum to an integer, what you're saying is SU3 times SU2 times U1 is not your gauge group, it turns out to be mod 6. And so, in the context of the standard, and then you can rinse and repeat. You can say, repeat the story for the up, and say, maybe this guy is always an integer, and all the complicated stuff is these two guys add up. So you have several constraints. You have this constraint, you have these guys rotated, which rotate it with different coefficients. It's not a 6, it's a third and a half. And for example, that case would you'd get mod Z3. You could say gluons are simple, and W and B are the complicated guys. You get mod Z2. And so what does this tell us? It tells us that the periodicity of theta of E and M, or hypercharge, is telling you about the gauge structure of the standard model. Which whole thing is all gauge invariant quantities in this guy have charge 1. All gauge invariant quantities of this guy has a multiple of 1/6, or 1/3, I guess. U1B 1/6. et cetera, et cetera. And so what, in the standard model, what it does is just tells you sort of quantization of electric charge in that sense. All right. Maybe went a little bit more on the deep end than I was planning, but it's fun, so I don't regret it. Anything else? All right.
Sorry, Anson, are there any observables distinguishing between the two choices?
Yes. So this guy here, notice this guy could have basically is saying the allowed value of this anomaly coefficient, A, because A, this is saying U and E and M is 2 pi A periodic. Notice in this case, E and M is 2 pi over 6 squared periodic. So if you measure 1/6 squared, it is definitely mod Z6. If each of these by themselves are integers, sorry, this one only couples, okay. I said it slightly wrong, but that's the basic idea. Is you said, this tells you the periodicity of theta, and this tells you which, these guys all have different periodicities of theta, Z2, Z6, Z3, Z nothing, and turns out that it's not like they're all mutually exclusive, but you can definitely narrow the list. I think, for example, I think this one has the smallest one, so you could measure this and exclude everything else. This one has the largest one, so if you measure this one, I think you end up getting them all.
So you're saying that the two are...
They have different periodicities.
No, even just from, I mean, suppose you knew that the standard model was all you had.
Yep.
Don't we know it's the bottom one just from...
Well, the standard model is all you have. We don't even know U1 is not R.
Sorry?
Well, in the standard model, if the standard model is all you ever have, then you don't even know that that U1 is an R or anything like that. In guts, we know this is the case.
Yes, that's...
If that's what you mean by standard model, yeah, yeah.
I mean, if it was anything other than that last one, you couldn't fit it in an SU5. Right?
Yeah, that's right. And so, for example, if you measured this guy, which is a periodicity of 2 pi over 6 squared, you've ruled out guts. Or at least guts in the form of connecting the standard model. Maybe they unify other stuff or some dark sector, but...
I love your definition of the standard model, Howie. SU5.
Are there any observational consequences in the absence of an axiom? Like,
in the absence of an axion, I don't know of any.
You always need to have some sort of non-local behavior going here. Yeah. That's what's provided by this string here.
Yeah. Yeah. So, okay. Let's see. More fun stuff with axions, strings, sure. Okay. Oof, I really am going slow. Dang it. Okay. So, one more fun fact about axion strings. It's a bit of a shame Ben isn't here, because otherwise I would have needled him a bit. But is the idea that axion strings have massless charged particles living on them. So if you have a string here, the claim is this guy has massless charged particles on it, and so it's a superconducting. So you have, this has massless charged particles. And so this is, turns out actually, there are complicated ways of seeing this and simple ways of seeing this. So let's write down the simple phenomenologist approach. Is you have a Lagrangian term. This works, okay, so I said charged, so I'm going to put FF tilde, but this could also be massless QCD charged particles for the axion. So for the QCD axion, you'll have massless colored particles, colored and charged. If you have an A over F, FF tilde, what I'm going to do is this says my equation of motion is d mu f mu nu is GA gamma gamma A, whoops, derivative of A f tilde, right? And if you work this out, if I put in an electric field here, the straight electric field pointing in roughly the same direction as the string, this is a current. This is J, and it is non-zero. A is non-zero because around here, the axion goes to axion plus 2 pi f. And f is non-zero because I just put an E field there. And you work out the directions. This says there's a J pointing radially here, and like that. In other words, current is flowing onto the wire at this point. Conservation of charge. You have something, current flowing to a point that's not moving. Charge of this wire is increasing as a function of time. So dq dt is not equal to 0. And so this means applying even the smallest electric field onto an axion string creates charge. And the only way for this to be consistent is if you have the Schwinger pair production that lets you produce particles along the line. Actually, it turns out to be half Schwinger, but not going to get into that. Okay, so this leads to quite interesting phenomenology. Basically, this says axion strings do not go as they please. They get hit by electric fields and magnetic fields, gluonic fields, very, very strongly. Like, this is saying, turns out, this statement is equivalent to the cross-section between an axion, a photon and a string being geometric in size. So cross-sections with sigma for a photon hitting a string is just 1 over omega, the frequency of the photon. So you get huge friction effects. Like if you had an axion string around today, it's not making it through the galaxy. It's stuck in the B fields. And these things are very warped by their environment. Okay. So I was originally, well, since Howie brought up guts, let's just very briefly talk about SU5, which is basically more of a warning story than anything else. Basically, if you believe in SU5 and axions, we will not see it, even if it's there. Why? Because of sociology, not physics. So, great. So let's very briefly go over this and justify why I said this. So if you had SU5, or really any unified theory, any gut, then basically at high energies, GG tilde is WW tilde is BB tilde times some normalization constant. Basically at high energies, gluons are W bosons, are photons, are everything. And so the only thing you can write at high energies in a gut symmetric way is the sum of these guys. Probably 3/5, question mark. Okay. And what this means is this is fixed entirely by symmetries, which means the way it couples to to the photon is fixed. This is 8/3 FF tilde. You have no choice in the matter. So this means for gut axions, we know exactly how they couple to photons. Which is GA gamma gamma, we said was alpha over 2 pi FA. This was E over N minus 1.92. This is 8/3. Take this difference. This is approximately alpha over 2 pi FA, roughly 30% times 1.92. So there's a small accidental cancellation, not even that small, 0.3. Why is this bad? Well, if you just look at where the bounds go when people plot GA gamma gamma versus the QCD Axion line, and let's blow it. Since there's some small thing, this is not even, that's identical in color. Let's choose green. This is the gut prediction. This is KSVZ, which is 1.92. And every experiment stops. ADMX stops. So they could be getting, okay, they might not have the dark matter density correct, but they could be getting the dark matter, everything else about their experiment correct, and they'll stop before hitting a gut.
How much longer would that take to iterate to cover that extra accuracy?
Okay, great. So we can do this. The signal power is going to be FA squared. The time goes the square root of t. So it's the fourth power, 3 to the fourth power, 27. So it's about 27 times longer. These experiments started in like 2000. Oh, 81. Oh, crap. That's even, yeah.
You've been doing great with all of your estimates.
Yes. So yeah, given that this takes years, and this band is not even order 1 in size, and it takes years, multiplying by 81 is bad news. They also assume a larger dark matter density than WIMP experiments do. So they also slightly cheat there to help make things look nicer. So maybe even for the KSVZ Axion, we won't see anything.
Can you remind me where the other Axion line is?
So then the next is the DSVZ,
Right.
which is slightly, it's fuzzier around here. It's basically a free parameter, but I think in the very original model, it's slightly larger. So that's basically what it only goes a little bit below here. But this is basically essentially what they're trying to probe is the DSVZ. Okay. Okay, so I guess since I already have this, I might as well transition into signal building. Okay, so let's redraw this in a, well, maybe not nicer, but a different picture. So what do the bounds on the axions look like? And what do I mean by signal model building? So there's two things you can do, GA gamma gamma coupling, where you have this fuzzy model dependent QCD axion line. Axion. And the bounds look roughly, let's do cast first. And a bunch of astrophysical stuff that Ben sort of mentioned down here. This is astro, this is, above that is the sun. And let's see, I guess then there are dark matter searches, which let's do them in orange. Different bands like that. Okay. There's this. So in other words, you can look for its coupling with photons, which doesn't actually prove that you're finding the QCD axion. Or you can look at the QCD axion coupling, which is the coupling to QCD. This is 1 over FA. So this is now QCD coupling, where there are actually a plethora of more bounds. So actually, this is not a dotted line. This is a solid thing. This is an exact prediction between the mass. This is QCD axion. And let's see. There is a sun constraint. Oh, should have done that in red. Okay. Sun. There are things like white dwarfs. There are, what did I do astro? Oh, I didn't put in stellar cooling. So here is supernova. There are, actually gets quite close to the Axion bound line here. There are neutron stars. And let's see, do I have another color? And you have LIGO from the neutron star merger. Okay. So this is basically what the field of constraints are right now. You can look for the photon coupling, which you have stellar type constraints. You can look for the QCD coupling. 20 minutes. Do people want me to tell them anything about any of these particular constraints? Or should we move on? Nope. All right. Let's see. Maybe, okay, maybe I might later on mention this since these types of things might, well, on a dream lattice would be nice to do, but I feel like finite density neutron star stuff in practice tends to be ridiculously difficult to do. Yeah. I guess if there's no sign problem, then chemical potentials become a lot easier. Okay, so let's see. So there are several things you can do from here. One is every single experiment that is being designed, at least in the US, it's very popular to propose new experiments and then draw very good exclusion bounds. And so they might be like, oh, let's say I have a new stuff that goes here, but after some upgrade could get all the way down. And the question is, are they looking for anything? In particular, so for this particular coupling, you can say you're not looking for the QCD axion. You're looking for any axion-like particle before you get to the QCD axion line. But as I said before, this line is fuzzy. And so you can ask the question, which is, are these guys, if they find something, could it be the QCD axion? Is it possible? Okay, and so this is sort of the question is just, this is what I'm calling signal building, which is on the way to the QCD axion, which is the one everyone cares about the most. Are you still probing any reasonable models? So models that live in any of these spaces, one up here, maybe to the right. Over here, it's the same thing. It can live to the right, or it can live up here. And so this is what I'm going to be calling the, I guess this is probably the last stuff I'll be talking about, which is signal building, which is models of the QCD axion that live in these different regions, 1, 2, to the right or to the left here. So I wrote these two the same because if you make it heavier, you just make it heavier. You can move both to the right. Playing with a coupling, making the coupling stronger is slightly different for photon or QCD couplings. Okay. So, great. Okay, so I guess I'm not going to talk about 2. Look at Tony's talk. He was basically doing it, I can't remember if it was yesterday or the day before. He was talking about how to make the axion heavier, moving it off the line over here. And the reason why you care about that is, I guess I didn't draw it on this particular one, but there are LHC bounds and things like that that live way over here. This is LHC. And so LHC is actually pushing down on the right-hand side. And so the LHC is more the one that's looking for these heavy guys here. So if you're, or beam dumps and things like that, basically all of collider physics is aiming for 2. new experiments that people are designing are aiming for 1 and 3. Well, they're aiming for the QCD axion, but they're getting 1 and 3 before you get to the QCD axion. Okay, so 2, see Tony. Okay, so 1 and 3. I guess 1 is 1, so let's do 1 first. Okay, so we had said before that William was done in Ben's talk when he did KSVZ, was what Ben said was you had a Lagrangian where, so this is the simplest approach. Y, phi, psi, c, where phi is gets some bev and goes as e to the I a over f. And this guy generates a coupling to QCD by the anomaly, but also I could just give this guy an arbitrary electric charge, right? If this has some charge QE, this generates an E squared A over F QE squared 16 pi squared FF tilde. And great, I can potentially take Q very, very large and move up and up and up. Now, what I didn't do was tell you the orders of magnitude on this plot. And this thing here, this is like 6 orders of magnitude. So you may or may not want to put charges of 1,000,000 into your theory. In principle, maybe it's possible, but you hit a Landau pole basically instantly. Well, I guess you hit a Landau pole because it's larger than, alpha is larger than 1 already. So you can't even trust much. But the main point is setting this large basically gives you a factor of 10 at best, right? Because Q squared times alpha should be less than 1. So this basically barely gives you the DSVZ line here, beyond the DSVZ. So you can go a little bit beyond, but you can't do it. So main point, you have to be tricky. Okay, so how have people decided to be tricky to deal with this? The main way they did it is something called the clockwork axion. Stems from the following observation. If you have an A over F over 16, 32 pi squared GG tilde. Okay, I'm going to stop writing G's. B over F 16 pi squared FF tilde. What else? Plus some confining scale to the 4th cosine 3A over F plus B over F. Okay, what does this do? This masses up this term. So you basically have 2 guys. One, you have an axion, QCD axion, and you have an axion-like particle. And this mixes them together a little bit. And so what happens when you start mixing new particles together? This means you have a massive guy, which is 3A over F plus B over F. And you have a massless guy, which is A over F. Maybe a minus sign, maybe a plus, whatever. And this is the guy, in the end, that you care about, because it's the one that ends up coupling to QCD and does great things. But what you'll notice is that as B, let's say, goes from 0 to 2 pi, this massless field shoots around 3 times, whereas A only goes around once. This is basically why they called it clockwork. You wind this guy up just a little bit, and this guy spins a lot more. So it's sort of like axles of a, hopefully I did this the right direction. Plus, and this will be 3 phi over F. Hopefully I got the right, I put the 3 in the right place. But And did I not write my notes? 3A, oh, crud. I had this, I think I had this backwards, but no. I think that's right, yeah. Okay, I actually did have it right. So you'll notice this has boosted the coupling, right? Because I swing this guy around 2 pi, this guy swings 6 pi, because B is the guy that couples here. And if you want to go as, so that just gives you a factor of 3. Okay, whatever. At 3, I could have just put the charge square root of 3 particle. But if I want to go parametrically farther, I just rinse and repeat. I say I have my A over F, larger B over F, larger C over F, dot, 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 where I now have cosine 3B over F plus C over F plus dot, dot, dot. And you basically just get 3 to the number of particles you've added in this way. Maybe n minus 1, if I have 2 particles originally anyways. Depends on how you count n. So this lets you basically get much, much larger couplings to the photon as compared to the gluon, and still be the QCD axion because the light particle only gets its mass from its coupling GG tilde. Okay, this is sort of the hoops you have to jump through to get this light, get this sort of signal. Turns out you have to jump through, if you thought this was cutesy but a little bit contrived, wait till you see what you have to do to get here. So, great, or maybe not so great. So, what do you have to do to live here? In other words, make the QCD axion lighter than the contribution from QCD, right? That's what, so why is this easy? Because this coupling, in some sense, has nothing to do with the mass of the QCD axion. Here, you're saying, I'm building an experiment. So the relevant one here being Casper Electric, which is a precession experiment to try to look for axion dark matter through the gluon coupling, exactly the coupling to the neutron EDM. What models are you probing on your way down here until you actually hit the QCD axion line? And the answer is, okay, so why is it hard? Because let's say I want to live here. I have a coupling here, and the mass, V of A, is minus m pi squared f pi squared, square root 1 minus 4 mu md over mu plus md squared, sine squared A over F over 2. Great. And that gives a mass that is, I think for this, let's just choose some numbers. So for FA of about 10 to the 11 GeV, I think, okay, MA of QCD is 100 MeV squared over 10 to the 11 GeV. Let's work in units of EV. This is 6, 7, 8, 16 minus, so this is about 10 to the minus 4 EV. To sit here, what you have to do is you sit about, I think that's about 4 orders of magnitude. The mass where you want to aim for, you're aiming for, is 10 to the minus 8 EV, which means you have to cancel this QCD contribution. It's not like, oh, I can set the axion mass to whatever it wants. No, this is solving the problem. And so to get here, you're introducing, if you want to just add a tuning, you're adding tunings almost as bad, sometimes even worse, than your problem you're trying to solve. Okay, so is it even possible to write something there that doesn't just by hand introduce a problem worse than what you started with? The answer is yes. We only have 5 minutes, so I'm just going to write down the answer for how to do it. So, great. So we're unfortunately going to, let's say we have some number of standard models, I equals 1 to, let's say, to n. And we're going to have a Zn symmetry exchanging them, which takes standard model under the Zn, Smi goes to Smi plus 1. So a bunch of copies of your standard model, and we're just going to impose that the axion goes to a over 2f plus 2 pi over n here. So what this means is you get a potential for the axion, which is n copies of this shifted off by 2 pi over n. The QCD, the a plus 2 pi pi over n, I equals 1 to n. And the claim is, by adding a bunch of QCDs, I've actually canceled the mass to a high degree, exponentially well. Okay, so how do we see this? First, we notice this looks like what? A sum f of x plus delta x times I is a Riemann sum, integral dx, some function of x, right? This is a Riemann sum. I'm just saying, adding them all up together, and you'll notice you're going to get, this is an integral from a to a plus 2 pi, or f over f, of your v QCD of x dx plus your error in your Riemann sum. And you'll notice I'm integrating a periodic field. My origin doesn't matter for a periodic integral. This doesn't matter. This doesn't matter. And so this is just equal to some number. So the entirety of the axion potential is in the error of a Riemann sum of a periodic function. And at this point, you go to your math friends and you say, tell me about this. Turns out, you could probably even find a precocious high school student who might know the answer, because it's there is a theorem about this called the Euler-Maclaurin theorem, which says the error, this error, the magnitude of it is less than 1 over some number to the nth power. In other words, this thing converges exponentially well. If you want to do, actually, people who've done the lattice will also have seen similar effects, where if you want to approximate a U1, a Zn approximation of a U1 works extremely well, basically for the same reason. This is the Euler-Maclaurin theorem. And the way you see this suppression turns out to be you make your angle complex, and you go off into the complex plane, and you see when you see analytic behavior. Moral of the story is you could also just do the damn thing. This ends up being some number times mu over md to the nth power times, roughly speaking, cosine na over f. And so you can see this is about a half. If I want to make the axion 4 orders of magnitude lighter, that's 10 to the minus 4. What 10 to the minus 4 is like 2 to the 13. So you'd have to choose n equals 13 about to do it. So
what's the, as n goes to infinity, what's the 1 relative, like what is that symmetry?
great. So as n goes to infinity, you basically get a shift symmetry for the axion, which is why its mass goes to 0.
Like in the standard one, it's a...
And there, as far as I know, there's no extra dimensional interpretation of this, because I'm not Higgsing any of these guys to the diagonal or anything up like that, right? I'm saying there are 10 copies of the standard model, all coupled only by this very weakly by the Axion, so there's 10 to the 11 GeV coupling to go into their sector, and then 10 to the 11 to come back. But I don't know of a good way to see this. Well, there is, okay, so one way to say why might I expect some exponential suppression maybe is you say this thing needs a potential, you mean you need n of these insertions of A over F. And you'll notice each one comes with, roughly speaking, if MD goes to infinity or large, MU over MD. And so you have to tailor a series up to MU over MD to get the nth power here. So that's sort of the sloppy physicist's argument for why this ends up happening. But yeah, it's basically, if you're hoping to do these experiments, you're sure, technically speaking, you are exploring stuff. In practice, you might just say, well, let's just hope I can very quickly jump down to the QCD Axion. All right, any questions?
Can you ever, in any of the parameter space that's available, populate with other sectors cosmologically?
No. You would have, well, if you got a reheat temperature extremely high, you could. The main problem with that is they're exact copies of the standard model. Standard model has a lot of degrees of freedom, so your N effective is going to be huge.
Yeah, that was my question. Are they just completely ruled out by cosmology?
Yeah, so the answer is basically no. It's pretty, you have to go to fairly high temperatures to thermalize the other sectors. Yeah. All right. Any questions? Other questions? All right. Yeah.
A question too that I put to Josh, which is
Yep.
that, for people in the audience who don't think about the KITP problem or axions, think about amplitudes or lattice, like what are the bridges from interesting questions in axion theory to other parts of the field?
So let's see. I'd have a few things. Let's say for amplitudes, I would say, well, two hallucinations would be one way of writing the axion is to say d mu A is epsilon d mu nu. And so given that you can write the axion as a two-form gauge field, is there some double copy, triple copy, whatever thing of relating gauge fields to axions? The second one might be, well, I don't know if amplitudes are the right thing, or just, are there other connections with the topological aspects? I think I find that to be pretty exciting. To be able to measure an ABGA anomaly directly is pretty cool. That's the only example I know of, but that may be just lack of imagination, and people will tell me, oh, there are actually other topological terms you can look for that have interesting effects. On the lattice side, I think the two things would be, well, like you said earlier, an ab initio determination of the theta dependence of the neutron EDM would be great. The other would actually be if it's possible to sort of better understand these neutron stars, since already actually all of these bounds on the neutron star here, which get sort of epsilonically close to the QCD axion, use sort of this nuclear sigma term, which is sum of the quark masses dm of the neutron or the proton, dmq. And basically, they use finite density effects. And so these finite density effects, if you're sitting far enough away, you can do them perturbatively using the help of some lattice terms. But it would be nice to know if a lot of these things have like additional theta dependence. So when people calculate the axion potential here, they say the finite temperature or finite density dependence is, we basically say it's the sigma nuclear times the number density times cosine A over F. This cosine A over F is in some sense just tagged on and sort of like, well, this seems like the reasonable thing, but it would be nice to know how much, like, maybe this depends on A and so the complicated dependence. And so it would be quite nice, well, quite nice. I think they would agree to be able to go to theta non-zero. But even just finding the theta dependence of terms like this would be interesting for us. Yeah. All right. Anything else? If not, we can go have cookies or in 5-10 minutes. All right.
Thank you.